Hello friends, in the last video we discussed about pipelining, a technique for parallel architecture or parallel processing. In this lecture we'll discuss few more techniques for parallel architecture. We'll discuss about multi-threading and also we'll discuss about vector processing as well as shared memory concept in this lecture. So without wasting your time, let's start the video. Parallel processing in this lecture. In parallel processing, we'll try to cover three different topics: multi-threading, vector processing and multiprocessing. These are the most important topics for your exam point of view as well. First of all, I'll discuss about multi-threading. What is multi-threading? Now, before we discuss about the actual concept of multi-threading, let me explain with the help of a real example again. Please pay attention. For example, say I have invited you to my cabin. You came to my cabin and I offered you a plate of your favorite food. So different types of foods I have kept in the plate and I offered the plate to you. Then Mr. X, please take this plate of food. This is for you. So you'll be very happy to take it because all the favorite foods are there in the plate. So you can easily take the plate in one hand. Fine. So immediately after that, I'm offering one more plate of maybe starters. All your favorite starters are there. So I'm offering one more plate to you. Mr. X, this is the second plate for you. So you'll be again happy because you have two hands, you can easily hold two plates. So after some time you can eat one by one. Fine, you are very happy. Now imagine after few seconds or 1 or 2 minutes, I am offering you one more plate full of sweets. All your favorite types of sweets are there. Now there is a problem. Why? You have only two hands. In one hand you are holding a plate full of your favorite starters. In another hand you are holding a plate full of your favorite food items. Now how you'll hold a third plate which is full of your favorite sweets? You cannot hold it. You have only two hands, right? Now in that situation, what you will do? You have two different options, or you have two different solutions maybe in your mind. The first solution is, what you will do is you will call your friend Mr. B. You will call Mr. B to come and hold any one of the plates for you, right? You can call Mr. B, please come and hold a plate for me for some time. This is one solution. If you are doing so, this solution is known as multiprocessing. Multiprocessor. You are using multiprocessors. You are asking a new person to hold the plate to help you to execute the same problem, same program. Fine. Now this solution is easy because you can easily call one of your friends, and of course whenever it comes for the food, anyone will come. But there is an issue also. What is that issue? Once your friend comes, you have to explain your friends what is this why your teacher is offering this food to you. So at least you have to explain the initial things to your friend, that these are the things, this is the situation, I cannot hold these three plates together, that's why I called you, please hold a plate for me. So you have to explain all these things to your friend, right? So this is an issue. You have to make everything to understand your new friend. Now what is the second option or second solution? The second solution is, if somehow you can create one more new hand for you. Just imagine you have two hands and you are holding two plates, and you can create one more hand also for you. Just like Dr. Strange. So you are creating one more hand and you are holding the third plate using the third hand. Things will be so good, right? No need to call your friend, no need to explain everything to your friend. Instead of that, what you are doing, you are creating your own hand and you are holding the third plate as well. So this second solution is nothing but multi-threading. You are creating a thread whenever necessary. Whenever two hands are not sufficient to solve the problem, you are creating one more new thread to hold the plate or hold the data or hold the instruction. You understood that? This is called multi-threading in simple word. I hope the theory is very clear for you. What is multi-threading? Fine. Now, whenever we talk about multi-threading in our computer system, we have two different approaches or two different techniques in multi-threading. The first technique is called coarse grained multi-threading. Now, and the second one is called fine-grained multi-threading. Now before I discuss about coarse-grained multi-threading and fine-grained multi-threading, let me explain again with the help of a real example so that it will be easy for you to understand. Now the same example I have explained in my classroom also. Suppose you have started a new drama company, so where you have hired some artists, some performers. They will perform their own things, own parts of their drama. Say you have hired 5 different artists, and every night or in every show they'll be performing their own parts in front of the audiences. Fine. Now to show their talents, to show the talents of all the 5 different artists, you have 2 different options. Option number 1, artist number 1 will go to the stage. He will perform his part of the act. He will finish his act. He will come back to the backstage. Then you will be sending artist number 2. Fine. Then artist number 2 will be going to the stage. He will be performing his act. He will be coming back. Then you will be sending artist number 3. Similarly, artist number 4 and artist number 5. Means you are allowing each artist to perform, finish his act. Then you are sending artist number 2, 3, 4 and 5. This is one type of way you can follow. Fine. Now again, when your artist number 1 is performing on the stage, maybe after performing half of his act, he need to change his dress or he need to change his costumes. For that he need to come back to the backstage and change his dress and costumes. Now what will be happening? In the meantime, if your artist number 1 is coming back to the backstage to change his costumes or dresses or whatever, your stage will be empty by that time, right? Your audiences will feel bored because no one is there on the stage at that time. So instead of that, what you can do is, instead of making your audiences bored, you can send artist number 2. You understood that? Because artist number 1 is taking some time to change his dress. Obviously, if the time is minimum, if he is taking only 1 minute of time to change his costume, then it's okay. Your audience can wait for 1 minute. You don't need to send artist number 2 to the stage. But if he is taking more than 1 minute, maybe 15 minutes, in the meantime, you can send artist number 2 to finish his performance. You understood that? If you are doing so, then this kind of solution or this type of technique you are following is similar with coarse-grained multi-threading. We'll explain with the help of some diagram also. Now in coarse-grained, can you tell me any disadvantage of this technique? Yes, there is a disadvantage. So assume that I have 10 different artists and each one of them are going and performing and coming back. What about artist number 10 or the last artist? Just imagine how much time he need to wait to get the stage. By the time he get the stage, maybe it will be already almost time to finish the show. Your audiences maybe already left the show. So it's very embarrassing for last artist number 10, right? Because it will be too late to get the stage. Artist number 1, 2, 3, they are performing and he is simply sitting and he is waiting for his time. So there is a drawback. The last artist will be keep waiting until and unless all the other artists finish their performances. So instead of following this technique, we have one more technique, which is called fine-grained technique. In fine-grained, what we can do is, we won't tell my artist 1 go finish and come back. Other than that, I will assign some time, say 5 minutes to each artist. Artist number 1, you go to the stage, perform for 5 minutes, first 5 minutes of your act, then come back. Immediately I will send artist number 2 to perform his first 5 minutes of act. Then artist number 3, 4, 5. So once all the 5 artists got the stages, at least for 5 minutes, then again I will come back and send artist number 1 again. You go and perform the next 5 minutes. If you follow so, somewhere we are doing a better things, right? Because artist number 10 or last artist will also get the almost equal opportunity to share the stage. Fine. This second option or the second technique is called fine-grained multi-threading. Now all these things we will discuss with the help of some diagram. It will be more clear for you. Suppose these are the threads I have. I have 4 different threads. for any particular program, thread number A, B, C and D. And in thread number A, I have to execute this set of instructions. In thread B, this set of instructions I have. Thread C, these are the set of instructions, and thread D, these are the set of instructions I have to be executed. Now using coarse grained approach, if you can relate with the your artist example here, can you tell me how I will follow to execute this whole program? I will first execute thread A. Once this is done, I will go for B, then C, then D. Fine. But can you remember I said one more thing also when I discussed about that artist example in coarse grain, that if your artist one is taking some time or some time to change his costumes or dresses or taking some unnecessary delays, then meantime I will send artist number 2. Same thing I will be doing here. So what I will be doing is, in thread A, I will send or I will start executing thread A first. So I will execute the first instruction, this one, second instruction, third, fourth and fifth. These fifth instructions, these 5 instructions I will execute first from thread A. In the meantime, B, C, D will be waiting. Now once these 5 instructions are executed, if you see here, this white box means some delay, means your artist 1 is going backstage and changing his costumes or maybe taking some time. So some delays, maybe for any reason, maybe for data hazard, memory hazard, for anything. So there are some delays. So I cannot afford this much delays. Otherwise my audiences will be keep boring. They will just leave the show. So what I will do is, once these 5 instructions are executed from thread A, since I have a long delay here or long gap here, instead of waiting for this delay, I will send my thread B or I will start executing thread B. So this one will be executed, this. I have a gap here, but a minimum gap. So one small gap I can wait for. So I will not skip this. After that I will execute all this. So all these instructions from thread B I can easily execute it. So once this is done, again I will come back here, because by that time it will be covering this delay. So now I can execute these 2. So once these 2 are done, then I will go for thread C. So in thread C, after executing the first instruction itself, I have a long gap. So instead of waiting for that, I will start executing thread D. So this thread D will be completed. Then I will be coming back here and I will execute thread C. This is how it works. Now see the solution. First, these 5 instructions I have 1, 2, 3, 4, 5. Fine. After that, what I said, I will start executing thread B because of long gap. So all these red boxes will be completed. All these red boxes will be completed. After that, what I will do, I will come back to solve these 2 last instructions from thread A. So these 2 last instructions from thread A. So after that, what I will do, I will go for thread C, and only one instruction I will execute, then I will go for thread D. So only one instruction from thread C, then I have gone for thread D because of this long gap. So once this thread D is done, then I will come back for all other remaining stages or instructions in thread C. So this is how it works in coarse grain. You understood that? Now in fine grained, what I said, in fine grained, I won't execute one by one like this. Rather than that, I will give equal opportunity or equal time for all the threads. So first, this instruction from thread A will be executed, then this instruction from thread B, then this instruction from thread C, then this instruction from thread D. See? So all the different colors I am executing. First this, second from B, from C, from D. A, B, C, D. Next again I will come back to A. I will execute this, then this. See here I have a gap, so I cannot wait for this. I will go for this directly. Then I will come here. Then I will execute this. Then I will execute this. Then I will come here. So like this, if you see the diagram, you will easily understand actually. You understood that? But if you have a long gap, you have to skip here also. So this is how fine-grained and coarse-grained multi-threading works in your system. I hope this is clear for you. Now we'll go for the next topic of discussion, which is called vector processing. Now what is vector processing? This concept is related to your instructions. So the another name of vector processing is SIMD, single instruction multiple data. Now let me explain what is SIMD. As of now, whatever instructions we know, how we deal with, say add R0, R1, load R0 to load A to R naught. Like this we have written all the instructions, right? Where in each instruction we are dealing with a single data. If I am writing load R naught comma A, means I am loading a single data from A to R naught, right? If I am doing add R naught comma R1, then I am adding single element from R naught and single element from R1, and I am storing to R naught only. So every time I am dealing with single data, as of now whatever instructions I have. Now it looks fine to deal with the single data. So whatever instructions we are dealing with, single data means SI as D we can say, single instruction, single data. Now it's fine to deal with, but imagine that you want to deal with some arrays. You want to add say 100 elements from array A and 100 elements from array B you have, and you want to add these all elements. Now how many times you have to write the instructions if you want to hold one data for one instruction? 100 different instructions you have to follow, right? Because instruction number 1 you are loading first data from array A, then instruction number 2 first data from array 2, instruction number 3 adding these two elements, again second data from A, second data from B, adding these two elements, again third data from A, third data from B, adding and storing. So for 100 different elements from the array A and B, if you want to add, then you have to write or you have to execute 100 different instructions, because your instruction can hold only one data at a time. So can we make our instructions a better instruction so that I can hold more than one data? Yes, that is called vector processing or SIMD, single instruction multiple data. Means here instead of holding a single instruction, a single data in one instruction, I can hold a set of data, more than one data. How many data? It depends on the application. It depends on L. L means how many data you want to store for the registers. Now your normal register cannot hold more than one data at a time. For that what you need? You need some special purpose registers, and we call it as vector registers. Fine, your vector register is capable to hold more than one data at a time. How many data? It depends on the program or application. It depends on the size of your vector register, how many data or how many bits it can store at a time. Fine, it depends on the value of L. L is the length of the register or how many data it can store. You understood that? Now how to deal with this kind of instructions where you are dealing with multiple data at the same time? This is how we write. So this is a keyword called vector add. Vector add means I am adding something. What I am adding? Vi, Vj, Vk. Dot s I am coming. Vi, Vj, Vk. So from this instruction I am sure you know that I am performing Vi equals to Vj plus Vk. From this add you can easily understand. Vi equals to Vj plus Vk. Now what is Vi, Vj, Vk? These are vector registers which can hold more than one data at a time. Means a set of data from Vj, a set of data from Vk I am adding together and I am storing in Vi. It may be 5 data at the same time or 10 data, whatever. Fine. Now what is this dot as all about? This as says for each data which are there in your Vj or Vk is the length of each data, or how many bits you need to store a single data from Vj or Vk. Say your Vj is holding two different integer numbers. This Vj or Vk is holding maybe integer numbers. For integer number, for each data I need how many bytes or how many bits. This as says that only. If you are dealing with integer number, then I need 4 bytes. If you are dealing with character, I need 1 byte. So this as is saying how much memory or how much space you need to store a single type of element from this Vj or Vk. So I hope this is clear for you. So this is how your vector processing works, and when it is very helpful whenever you are dealing with some kind of array or some kind of vectors, right? So let me take one example, it will be helpful for you to understand. Suppose I have a program in front of you. What is that program? For I equals to 0, I less than an I plus plus, ai equals to bi plus a. Whatever I said, that you have some set of data in array B, you have some set of data in array C, and you want to add all this data, and this is the program you have. If I ask you to write this program in C, this is how you will write, right? Now to actually execute this, if you have say 100 different data, then how many times you have to execute, how many times your for loop will be running here? 100 times, right? 100 times this loop will be keep running. So 100 times this set of instructions will be executed. Please read this set of instructions once. This is not new, we have already gone through this kind of instruction. This is a normal instruction, this is not a vector instruction, where what I am doing, n is nothing but number of elements which I am holding in R5. Then the first data from array B I am storing in R6, first data from C I am storing in R7, then I am adding these two data and storing in R6. Fine. Then what I am doing, this result, whatever the second, whatever the result is there, I am storing in R6. Fine. And after that, what I am doing, I am adding R2 equals to R2 plus 4 because I am dealing with integer number. So to get the next address of the next data, I have to add with 4. Similarly for C array also I need to add with 4. Fine. So this is how this loop will be running 100 times because R5 equals to R5 minus 1. So from 100 it will become 99. It will be keep looping 98, 97, 96, like this it will be keep looping until and unless it is equals to 0. So 100 times you have to execute this instruction. So how lengthy your program will be, how much time it will take. Instead of that, what we can do is we can write vectorization or we can write SIMD. So if you do that, how it will look like, this is how it will look like. So now what I will do, if I write V0, R3, I am not storing a single element to V0. Load L elements, maybe 10 elements from array B I am storing to V0 at a time. V0 is holding 10 elements from array B. V1 is holding 10 elements from array C. Then I will add all these 10 elements. Now first 10 elements are done in one loop only. So if I do so, how many times I have to run this loop? 10 times, right? Because in one loop I am adding 10 elements. In second loop 20, third loop 30, 40, like this. If I run this whole program 10 times, I am adding 100 different elements. I hope you understood the concept. So see the difference. The same program, if you use normal instruction, then you have to run this loop for 100 times. But for vectorization, you have to run only for 10 times. See the time gap. Fine. This is how vectorization works. Now the next topic of discussion is called shared memory multiprocessors. So again, before I jump, this is a simple concept, but before that I want to take one example. Say you want to run a huge program, the program size is very huge, very complex, very hard program you want to run, and for some reason it may happen that your single processor is not capable of running the program because the program is very huge. One processor is unable to do that. In that time, what you will do? The solution is you can combine multiple processors. You can hire some other processor, maybe 3-4 processors you can make use to work for a particular program. Because the program is very huge, you cannot use only one processor. Fine. Maybe you have combined 5 different processors to solve a particular program. That is fine. Now from where it will get the data, from where it will be executing, from the main memory, we know that. Because the common program or same program is running by all the different processors, you need a same shared memory space also, from where every processor can take the data. Fine, this is called shared memory concept, where multiple processors are working to solve a particular program using the same memory space. Fine, obviously it needs the same memory space because the program is common program, it's single program, it's not multiple programs. So for that, we have two different architectures to share the memory. The first one is called UMA, Uniform Memory Access. So here what I will do is, see here I will have multiple processors P1 to Pn, and I have a memory space. This is a common memory space. What I will do is, this common memory space I will make some small slots like this, so that whenever P1 want to access some memory space, it will be getting from M1. P2 it may go for M2, MK, and every processor is able to communicate with any one of these memory slots. This is a common memory space only, but I have divided into multiple slots. Now why it called as uniform memory access? First of all, I have multiple processors, right? P1 to Pn. and I have multiple memory slots also, M1 to MK. If you see here, in between I have an interconnection network to get the data. If you see the diagram, it seems that P1 is closer to M1. Means if P1 want to access something from M1, it will get easily. It seems like that. And Pn, if you want to access M1, it seems like it's very far. So it may take some time to get this data from M1. It seems like that. But uniform memory access says all the processors need the equal time to get any data from any memory access. Means if one clock cycle is needed for P1 to get something from M1, for Pn also the time requirement is one clock cycle only, not more than that. Same amount of time it will take. That's why we call it as uniform memory access. In this architecture, one more thing we have, there is no concept called boss and client architecture. Every processor gets the equal preference. They have the equal probability to get the data. There is nothing called someone will be client, someone will be server. No, everyone is same. Fine. So this is the architecture of UMA. So I hope this architecture is clear. Now the second architecture we have called NUMA, non-uniform memory access. So what it is? In the previous case, obviously for each processor I know I need some memory slot. But for that I need to visit here, right? So can I make this architecture in a little bit better way? Yes, I can do that. What I can do is, I know all the processor will be needing some memory space by default. I know that they need some memory space. So what I can do is, for each processor, immediately I can attach some memory slots. P1 with M1, P2 with M2, Pn with Mn. So that now if P1 needs something from M1, it will get immediately here. No need to go through any interconnection network and search it. No need to search for the address and all. Means if P1 want to access M1, it's very faster now. Fine. Now from this diagram, don't be confused. This M1 can be accessed by P2, P3, Pn, anyone. This memory are already in shared space. Anyone can access this M1 or M2 or Mn, but the only change I have done is this M1 I have fixed with P1, so that P1, if P1 needs some primary memory, it will access M1 directly. No need to go through any interconnection network. If P1 need M2 also, obviously it will go through interconnection network and it will get M2. It can access any memory slot, but M1 is faster for P1. But now in this diagram, if you see carefully, this time requirement is not same now, right? Because M1 is fixed or attached with P1, so P1 will get in a very faster way than P2 or Pn, because Pn should go through this interconnection network to get M1, but for P1 no need to go through any interconnection network. Because this time requirement is not same for all the processor to get any particular memory slot, that's why we call this architecture as NUMA, non-uniform memory access. Fine. So I hope all this concept is clear for you. Thanks for watching the video.